regions that are not simply connected, and what I'm rather colloquially calling regions that have holes. Okay, could you please keep quiet? I'm just referring to those of you who are chatting. Please stop talking. For non-simply connected regions. Okay, if you could please keep quiet. Okay, so yesterday I justified the fact with showing you regions that had that shared a piece of boundary curve, and justified it wasn't a very particularly formal proof, but hopefully was convincing that Green's theorem can still apply to regions that are not simply connected. So first of all, I'm basically going to demonstrate with two examples. And the first example is a region that comes with a hole already in it. Okay, so region that comes with what I'm calling a hole. Okay, which I don't think is a term that you'll find in a formal textbook. And that is exercise 39. It says, find the line integral x cubed minus y cubed dx, x cubed plus y cubed dy, if C is the boundary of the region between these two circles. Okay, so we've got a circle of radius 1 and a circle of radius 3. That's a 1, that's a 3. Here is the region I'm going to look at. And C is the boundary, okay? So I'm going to call this one here C1, and I'm going to call that one there C2. Note the direction of the arrows. And the C that I've been given is the union of those two, okay? So the boundary of that region is actually two circles. It's the union of those two circles. But it's all been given to me. I don't need to do any puzzling over what's going on. The region's been very clearly described, and I can just jump straight into doing Green's theorem, where I call the region between the circles D. And it's dq by dx minus dp by dy. dp by dy has a minus, so when I subtract it becomes a plus. And both the integrand and the region are both very encouraging of a coordinate change here. So I'm going to pull the 3 out. My integrand is x squared plus y squared, which is r squared. My dA is r dr d theta. R goes from 1 to 3, theta goes from 0 to 2 pi, and that's a very easy integral to work out. So what will that be? That'll be 3. Very hot in here again, isn't it? Were you in here yesterday for any lectures later in the day? Not. I wonder what it was like. Probably not very nice. Okay, we have r cubed, so that'll be 1 over 4 r to the 4 from 1 to 3, and that'll just be a 2. The theta will just contribute 2 pi. Let's have a look. 3 to the power 4 is what? 81. So it's 81 over 4 minus 1 over 4. That's 80 over 4. That's 20. 20 times 2 is 40, times 3 is 120. So that's 120 pi. Okay, so there's no thinking required. We've been given a region that has a hole in it, and we say, well, that's fine. We're not going to worry about it. As long as the curve C is the entire boundary of the region, then everything's fine, and we can just apply completely vanilla Green's theorem. No, nothing fancy required. Question? From this line to that line. This thing over here. Okay, let's have a look. This thing over here is Q, and this thing over here is P, and this is dq by dx, and that's dp by dy, except actually it's actually minus dp by dy. Make sense? Cool. Where you identify Q as the thing that's sitting in front of the dy, and you identify P as the thing that's sitting in front of the dx. And usually it's written with the dx bit first and the dy bit second, but it needn't necessarily be. Okay, and in fact, I gave you something very like that earlier on as well with exercise 33 without at the time raising that it was an issue. All right, but then we move on to the stickier kind. Exercise 40. I have been informed by those who are more familiar with engineering than I am, because my background is not in engineering, that the sort of exercises represented by 40, 41, and 42 are particularly relevant to electrical engineering students. I'm not sure why. I don't know why. You'd have to ask your electrical engineering lecturer. Is something to do with singularities. I'm not sure. In fact, I should ask one of the electricals and then I would be better informed, but I haven't got around to that. Okay, so what have we got? We've got this rather funny looking thing here. Okay, so I've got my P and I've got my Q, and then C is that square path. I must admit I haven't been given a direction, but if the direction isn't given, you assume by default it's positively oriented. So there's my Y, there's my X, here's my C, and I want to work that out. Now I can work that out. That's not too bad, except for the fact that that line integral is actually going to be 4 line integrals, because I'm going to need to do it on each of those line segments. However, each of those line segments will be very easily parametrized. It's probably not that too bad. Probably not too bad an integral. The integrand would quite like a coordinate change, but the region is not particularly, but we wouldn't do a coordinate change for a line integral anyway, really. Yeah, so you could do that as a line integral. A little bit of effort, but it'll be a lot easier if we could use Green's theorem. A lot easier if we could use Green's theorem, because our regions are square. Also, when we work out our dq by dx and our dp by dy, they'll be temporarily messy because we'll have to use quotient rule. Where'd I come with squeeze theorem? Sorry, a bit of a mind blip there. We'd have to use quotient rule. So they'd be temporarily messy, but actually it would simplify quite nicely. So Green's theorem would be absolutely delightful, except for the fact that our P and our Q are not defined at the origin, because we'd have division by 0. And if you read the wording of Green's theorem, it says that P and Q have to have continuous partial derivatives throughout the region, and in fact a little bit outside the region as well. And if the function's not defined, then it doesn't even have derivatives, let alone continuous partial derivatives. So we have a problem. We'd like to use Green's theorem, but the region doesn't really allow for it. So what we can do is we can introduce a new curve. So let's just write here. Want to use Green's theorem. P and Q are not defined at the origin. Okay, so what we're going to do is we're going to introduce a new curve, which we are going to design. It can be any shape, but circular is good, and I'll come back to that later. We introduce a new curve around the origin and define our region as the area or region between the two curves. Okay, so into my drawing I'm going to put a new little curve. Okay, now there are good reasons to make that curve a circle. It can actually be any shape you want, but later on we're going to have to actually do a line integral along that curve. So keeping it a nice simple curve is to our own benefit, and a circle is a nice simple curve. Of course, so what we're going to do is we're going to use Green's theorem. We're going to use Green's theorem. Now Green's theorem says that a line integral along a boundary curve is equal to a certain kind of double integral over the region bounded by that curve. But in order to use Green's theorem on this region here, the boundary of this region is not just the outside curve. It's the union of the outside curve and the inside curve. So if I carry out Green's theorem and I do my double integral over that region, I'm not getting the line integral that I want, which is that thing there. I'm getting the line integral I want plus the line integral along that inside curve, which I don't want. So what I'm going to do is, after carrying out the double integral part of Green's theorem, I'm then actually going to subtract out of my answer the line integral that I'm actually not interested in, which is the one along that inside curve. So I'm not going to avoid doing line integrals altogether. I'm just going to avoid doing the line integral along the curve I've been given. I'm still going to carry the burden of a line integral along that inside curve, which is why it's to our advantage to make it a nice simple curve. Okay. Given that I'm going to do a line integral along that inside curve, it's a circle. I'm going to parametrize it. Circles are very easy to parametrize. X equals r cos theta or cos t, y equals r sine t. But that parametrization that I've just rattled off is anti-clockwise. And I don't want my inside boundary curve to be anti-clockwise. I want it to be clockwise, so that it's positively oriented, because Green's theorem demands that. So what I'm going to do is, I'm going to call this curve on the inside, I'm going to call it C subscript r. And I am going to parametrize it the normal way, which means it is going to go around anti-clockwise, which is undesirable. And I'm going to call my region D, and the boundary of D, sorry, this is getting a little bit scruffy here, let me use a different color so it stands out a bit better. The boundary of D, the positively oriented boundary of D, is C union minus CR. Okay, now even if all that stuff I was talking about, and I was saying double integrals and line integrals, even if that, you listened to that and you thought, I don't have a clue what she just said, I hope you can agree that given that the arrow on the inside curve is going around anti-clockwise, I hope you can agree that the positively oriented boundary of my region is the outside curve union with minus CR. Because we want the boundary of D to be positively oriented, and CR is not. CR is going in the wrong direction. Okay. Phew. Right. Okay, and then a little note on that, just for when you're reading your notes again afterwards, because I've said a lot, but it's not written down. We design CR, a circle, actually, let's take that comma away, a circle of radius r, where the radius can actually be anything as long as it's small enough that it sits inside the square. So let me just say where r is small enough to fit inside the square. Defining CR the conventional way results in anti-clockwise parametrization, or an anti-clockwise direction. So positively oriented boundary of D is our original C that we were given, union with minus CR. Okay, now I'm going to do Green's theorem. So there was a lot of chit-chat there, and I said a lot of stuff that was quite information dense, so I wouldn't be surprised if you didn't pick up on it all, but I'm going to do the calculation and then hopefully it'll all come clear. So, let me skip a line rather, so that what I'm doing is clearer. Rather than using C, I'm going to use that symbol for boundary of D, that little sort of delta D thing. Well, that's not really a delta, that curly D. And that is that, according to Green's theorem, I can turn it into this. So let's do that. No. Over there. Oh, you mean because my original thing's got a minus in it, does it? Does it? No, it doesn't. I think everything I've written there is correct. Okay, so let's work out dq by dx and dp by dy. Q is, what's Q? Q is x over x squared plus y. So dq by dx is going to use quotient rule. Quotient rule says derivative of the, we differentiate with respect to x, remember. So y is just a funny looking constant as far as x is concerned. So quotient rule says derivative of the numerator times by the denominator minus derivative of the denominator times by the numerator all over the old denominator squared. So that looks pretty horrible, but don't worry, things do simplify. So what will I have there? That's rather wiggly. Let me tidy that up. That's a 2. So I'm going to have x squared plus y squared minus 2x squared. So that's actually going to be a y squared minus an x squared over x squared plus y squared squared. Okay, let's work out dp by dy. So p is what? P is minus y over x squared plus y squared. So dq by dy, once again I'm going to have to use quotient rule. dp, thank you, thank you, thank you. Sure, all these p's and q's and x's and y's. Okay, quotient rule says derivative of the numerator times by the denominator minus the numerator times by the derivative of the denominator over the old denominator squared. So I'm going to have minus x squared minus y squared plus 2y squared. So I'm going to have y squared minus x squared. The two derivatives are actually the same. So when I subtract them, I'm going to get 0. Question, yes?
For q, the first little term which got there, is it x squared plus y squared multiplied?
Thank you. I copied badly. Okay, it's quotient rule. It's partial derivative quotient rule. So you've got to keep in mind what variable you are differentiating with respect to, but other than that, it's just quotient rule. A little bit of tidying up, and you'll discover that dq by dx minus dp by dy is 0. In fact, our big F, represented by p and q, was actually a conservative vector field all along. Interesting. But that not defined at 0 is an important thing. Yes?
I think the thing Michael was asking earlier, why we don't have minus, what do you call it, the p, dq, dx, and dp, dy, is because in 39 we wrote above the second line that it was a minus.
Did I write my Green's theorem incorrectly?
Yeah.
Because that was minus a negative. So it was 3x squared minus 3y squared.
So why are we adding dq, dx, and dp, dy this time?
No, we're not. We're subtracting. In 40,
Yeah.
we are subtracting. There's a subtract. But those have a plus. That's just the formula for Green's theorem. It's a confusing. There's letters and integrals and subscripts, and it's quite symbolic heavy. There's kind of like quite a large sort of cognitive load reading that, because there's just so many symbols in so many different places, and every single symbol means something different. Okay, so this, let me come back to the original. So therefore, the line integral, there's a minus. Is equal to y squared minus x squared over x squared plus y squared all squared, subtract y squared minus x squared over x squared plus y squared all squared, which is the double integral of 0, which is 0. Lovely, how nice. Except, of course, that that's not what we want. That's not what the question asked for. The question asked for the line integral along C. The question did not ask for the line integral along C union with this other thing. I've come to the bottom of a page, so I want to do a page jump, but I'll pause. So what we're going to do now is I'm going to split up that line integrals on the left. The line integrals on the left are going to split up into the one that I actually want along C, plus the one that I actually don't want, which is the one that along CR or minus CR. And then I'm going to take that CR one across the equal sign. I'm going to actually work it out, and I'm going to remove it from my total. Question?
Doesn't the integral of 0 equal a constant?
It would if it were an indefinite integral. If it were an indefinite integral, but this is not, this is a definite integral. So there's no plus c involved.
Just because in previous examples that I've been doing in the book, I've been working like that and I've been getting correct answers.
Okay, I'd like to see if maybe we can talk separately. You can show me what's, but the integral of 0 is 0. And you can think of that in terms of we're working out the volume underneath a function when the function's actually lying on the ground, and then there is no volume underneath it, so the answer is 0. So there must be something special about those examples that you're talking about. So, cool. Okay. So the integral that we're actually interested in is this one. And it's going to be equal to 0 subtract the one that we don't want. Okay. So what I'm going to do is, a little bit of sleight of hand here, that integral is along the curve minus CR. I'm going to actually make it along CR. I'm going to change the direction, which means I change the sign of the integral. Okay, now I've been chatting all this time about CR, but I've never actually parametrized the curve. Now is a good time to do that. So let's parametrize CR. I've said it's got some unknown radius r as long as r is nice and small. So we've got r cos t, r sin t, t going from 0 to 2 pi. So we actually need to work out that line integral now. We can't avoid it any longer.
Sorry.
Yes?
What trick did you say you used to get rid of the minus sign?
I change the direction of the curve, and you could always change the direction that you're going, but then you flip the sign of the integral. Ooh, this is bad form. This equal floating in the middle of nowhere. Very bad style, but I'm going to carry on anyway. And I'm going to put everything in terms of t's now. So this is going to be 0 to 2 pi. What was p? P had a minus y, so minus r sine t, over x squared plus y squared. X squared plus y squared is going to be r squared cos squared plus r squared sine squared. That's just r squared. Catch up with me, stylus? Thank you. Dx, well, what's dx going to be? Dx is going to be, what? Minus r sine t. And then the q, and then there's also a dt, but I'm pushing the dt to the end. And then my q has an x at the top, r cos t, over x squared plus y squared, which once again is going to simplify just to r squared. And then my dy is r cos t, and I'm going to dt at the end. Okay, all right, so what's happening here? Let's tidy up. I'm going to have an r squared sine squared over r squared. Okay, I could do this I could skip steps, but I'm not going to, so that you can see what's going on. And the r's actually cancel. So it didn't actually matter what we made r. We could have set r to an actual number, a half, a quarter, a tenth. It ends up not matching what r is. And sine squared plus cos squared, of course, is 1. And that's just 2 pi. And that's my answer. So that's the answer to the question. The question said, what is the line integral along C? That's what it is. It's 2 pi. Notice that F equals PQ is a conservative vector field if P and Q had actually been defined throughout the region and a little bit outside the region, then I would have been able to use Green's theorem without this funny construction of an inside path, and I would have just done the double integral and I would have got 0, which is what we expect. We expect the work done along a closed curve in a conservative vector field to be 0. But the exception to that is if the components of the vector field are not fully defined throughout that region, in which case you have to do this funny little curve story, and what we end up with is, in fact, for any closed curve, C, not, I see I've written here passing through, that's not what I mean, I must change the wording in that, not encircling, I suppose, the origin, or containing, perhaps, containing might be a better word, encircling, actually, no, I'm copying the wording from my notes, but the wording from my notes is actually very bad wording, so let me, for any closed curve C, the line integral C p dx plus q dy is going to equal 0 if C does not enclose the origin, and 2 pi if C does enclose the origin. Okay.
Sorry,
Yes, question.
is this just for curves where the vector field is not defined at the origin?
Or it's for some point within the region.
Okay, so this only applies to like Holy functions, as it were, not or regions, or vector fields, not.
So this little brackety story that I've just written here applies to this particular function,
Okay.
because this particular function had a problem with the origin, although I think you'd find it would still, you'd still end up with 2 pi. You'd still end up with this result for any curve that encloses a region where the conservative vector field is not defined, but the only change would be it might not be the origin, it might be a different problematic point, but you'd still end up with that 0, 2 pi pattern. There was a question?
What do you mean by C does not enclose the origin?
So if we'd had this exact same P and exact same Q, but the curve had actually been something off in the first quadrant, not around the origin, then we would have ended up, we wouldn't have had to have designed that CR. We would have jumped straight to the double integral and got 0. Which is what you expect, particularly if you look at the, I mean, it's in that decision tree. Now, of course, in those decision trees, I haven't put all the terms and conditions. And there are always terms and conditions. But you'll see it says, is C a closed curve? Is F a conservative vector field? Yes, yes. The answer is work equals 0. That's what you'd expect. But there are little hidden terms and conditions which this problem ran into, which is not defined at a point within the region. Okay, so these are quite tricky problems. And at this point, I would really like to give you the opportunity to work through one, and I would like to ask you to do exercise 41, but we're a lecture and a half behind our schedule. So I can't do that, and I need to move on. Okay? But exercises 40, 41, and 42 are all the same sort of thing. Okay? What I'm going to do is when I put up the solutions to 40, I'll put up the solutions to 41 as well. 42 is assigned to the next tutorial. Question?
When we look at the question, how would we know that we need to do this first?
Because you'd recognize that your P and your Q are not defined at a point within your region. So you just got to keep in mind, it's as I say, they're the sort of terms and conditions. Green's theorem only applies for positively oriented curves, that's important. And your vector field needs to have continuous partial derivatives throughout the region and even slightly outside the region. And that can be very easy to forget because so many functions do fit that we forget that occasionally you run into functions that don't. They always look funny though, because they always result in a division by 0, so they're always slightly funny looking functions. As you'll see in 41 and 42, they have that sort of division look to them, with the danger of division by 0 built in. Okay, all right. Stokes' theorem. I'm actually going to open a new document. Let's talk about Stokes' theorem. All right, I went through a phase of typing my notes up neatly. Did I ever type up Stokes' theorem neatly? I wonder. Oh, apparently I did. Yay. Okay, Stokes' theorem. I'm probably only going to get the sort of wordy bit out of the way now. We'll probably only find time for an example on Monday, but at least we can jump straight in. Stokes' theorem. Let's change from green. Blue, purple, black, red. Red. That was cheesy. Stokes' theorem. Note the position of the apostrophe. It's not named for somebody called Stoke. It's named for somebody called Stokes. So you put the apostrophe after the S. You can get it right. I know you can. Okay, so Stokes' theorem is very, very similar to Green's theorem, but it just steps it up. Well, not a dimension so much. Instead of our regions being flat regions in the coordinate plane, we're now going to be looking at regions that are actually pieces of surfaces. Okay, so Green's theorem relates a double integral over a region to a line integral along the region's boundary. Stokes' theorem relates a surface integral over a surface or piece of surface to a line integral along its boundary, which will be a space curve. Okay, so I'm going to give you the statement of Stokes' theorem, but I'm sure it's in a box as well. Stokes' theorem, it's written in a box on the bottom of page 67, so what I'm about to write is printed in the handbook. It says, let S be an oriented, so S is a piece of surface, okay? And by oriented we mean we're defining it as having a sort of a top and a bottom, or an outside and an inside. We are considering it to have a directionality in a sense. Let S be an oriented, piecewise smooth, meaning it can have corners, but just has to have a finite number of them, surface that is bounded by our old friend a simple, closed, piecewise smooth boundary curve. All these adjectives. Bounded by a simple, closed, piecewise smooth Putting the hyphen in the wrong place. It should be between piecewise and smooth, not between piece and wise. Oh well, whatever. Piecewise smooth boundary curve. And here I am being fussy about punctuation, and then I put my hyphen in the wrong place. Hypocrite. Here we go. Curve C with our old friend positive orientation. That should be a with. I'll come back and fix it. Positive orientation. Let F be a vector field. So quite similar to Green's theorem so far, whose components have, you guessed it, continuous partial derivatives. On, you guessed it, an open region. In R3, because even though a surface is really a two-dimensional thing, they're floating in a three-dimensional space. Okay, so in R3,
What do we mean by an open region?
it means it's got to include your region, but then also slightly outside it as well. It means you need to be able to draw a dotted line that includes the bit that you're interested in. Open region, dotted line. It's a thing in pure maths. It's a thing. Which, I've lost my place. Which contains S. Let me go back and change that funny word over there. With. Then, and here's our formula. F dot dr, which is what PDQ, PDX plus QDY was. It was an F dot dr. It was just a two-component F, and here we're going to be looking at three-component Fs. So this thing I've written down is also what we saw. This is going to be PDX plus QDY plus RDZ. And this is equal to, and now here's where it looks quite different from Green's theorem. Okay, two integral signs, yes, but it's a surface integral, not a double integral. Curl F dot ds with an arrow on top, and that's just another way of writing surface integral curl F dot unit vector ds. That is a capital S. That is the formula for Stokes' theorem, which you need to know off by heart. I'm not even going to pretend to derive it. One amusing story is, it was a couple of years ago, in February during registration, for some reason there was this whole long line of third-year students all along my corridor having to get some forms signed at the end of the corridor. So there was like 60 students all along. And so they were all sitting with their backs against the walls, and then every now and again inching up as the next person got their forms signed off. So I took Stokes' theorem and I wrote it on a piece of paper and I stuck it to the wall underneath the window opposite my office so that they'd have a beautiful formula to keep them entertained while sitting there. I'm sure it cheered them up immensely to see their old friend Stokes' theorem. That's a pretty cool theorem. I mean, look at that. It's got single integrals and double integrals and triangles and arrows and cuppies and all sorts of dots. It's got everything you might want in a maths formula. Except maybe complex numbers, because they always make every day brighter. But unfortunately, we don't have that. So one thing I miss teaching second year maths is no complex numbers. In the special case, because if you think about it, a region that's lying flat on a coordinate plane is really just a special case of a surface. I mean, it still is a surface, just happens to be a surface that's just lying flat on a plane, but it's still a surface in a sense. It's a portion of the plane x equals 0 or something like that. So in the special case, where S is a flat region in the xy plane, or really any of the coordinate planes, then our n will just equal k. Okay, so if we think of our special case, where our surface is actually just a flat region, a lamina lying flat on the xy plane, the normal that's orthogonal to it would be k, would be 0, 0, 1 pointing straight up, which means we take our curl and we dot it with 0, 0, 1, and then we flip back in our notes to where curl f was on page 63, and we'll see that if we take curl f and we dot it with 0, 0, 1, we get dq by dx minus dp by dy. And of course our surface integral will just dissolve down into being an ordinary double integral. And so we would have, if we take our Stokes theorem formula, which is this thing over here, our curl f it's a vector, it's got 3 components, but now we're dotting it with the vector 0, 0, 1, so we're left with just the third component, and the third component is dq by dx minus dp by dy. And in the special case where your surface is actually just lying flat on a coordinate plane, or in fact parallel to a coordinate plane, your surface integral is actually just an ordinary double integral. Green's theorem is hence a special case of Stokes' theorem. And so in some books it's presented that way, and I know in some vector calculus courses it's chosen to teach it that way. You actually teach Stokes' theorem first and then get Green's theorem as a special case. Green's theorem is hence, bless you, a special case of Stokes' theorem. Okay, I'm going to stop there. Next I would like to do some examples, but I'll obviously save that for Monday. I see I've given myself 3 to do here, presumably the first 3. So I'll do 43, 44, and 45 on Monday, and then you'll give 46 and 47 a go. And if you want to think of this course as climbing a mountain, and then you keep thinking you've got to the top of the mountain, but in fact the mountain keeps getting higher, Stokes' theorem is the top of the mountain. And after that, it's grand slalom down to the finish. So once you have managed to conquer Stokes' theorem, you can feel mighty.